In this next chapter, we're going to discuss applications of the definite integral and the fundamental theorem of calculus to velocities and rates. In this lecture, we're going to concentrate on velocities, the displacement, the position, and acceleration function, and then we're going to extend our analysis to other rates of change. So let's first of all recall the fundamental theorem of calculus, which states that if f of x is any antiderivative of my function little f of x, then for the x in the interval between a and b, the definite integral can be computed as the value of the antiderivative at the right-hand point minus the value of antiderivative at the left-hand point. Let's unpack this just a little bit to remind ourselves why this result is so useful. So what does it mean to be any antiderivative of f of x? What does this statement actually imply? Well, antiderivative means that the derivative of capital F of x is actually little f of x. This is an important thing to remember in order to access all the word problems that are associated with these ideas that we're going to discuss shortly. So that means I can rewrite this integral in terms of the capital F of x. So what I'm going to have is the integral from a to b, and instead of f of x, let me just actually relabel them x's because it really doesn't matter. What I can then do is replace f of x, the little f of x, with what it means to be in terms of its antiderivative, f prime of x dx. And the right-hand side I'm going to leave as is, f of b minus f of a. So what we notice now is, of course, what justifies the terminology. The integral and the derivative basically cancel each other out, and we are able to produce an expression purely in terms of this capital F function. On the other hand, we can think of what does each side of this equation actually represent. On the left, we have the integral of the rate of change of this function f. And on the right, we have a net change that occurred in f over the interval between a and b. I take the finished value minus the start value of this function. This observation is really useful in order to understand how, for example, things like displacement, position function, velocity, and acceleration are connected to each other. So let's summarize this once more time. Integral of the rate of change on the left-hand side over some interval from a to b is equal to the total change over that same interval. What is also important to note here, though, is that this total change is actually net change. So the end value minus the beginning value without necessarily including anything that happened in the middle. And this is something we're going to have to be a little bit more careful about. So let's talk about displacement, velocity, and acceleration. If I allow x of t, so of time, be the position of some particle, let's say, this is generally a very physics-motivated application, then I'm going to denote v with its velocity and a, the acceleration. If you remember this from Calculus 1, then this will sound familiar, that the derivative of the position function is actually the velocity, and the derivative of the velocity is actually acceleration. So that means that as I'm going down this list, I can be taking the derivative in order to produce the next function. I take the derivative of the velocity to produce the acceleration, and if I'm going up in the direction from acceleration to the position, in order to get velocity from acceleration, I will be taking an antiderivative, and to get the position from velocity, I will also be taking antiderivative. So this is the connection between these three. X of t is an antiderivative of v of t. So that means that I can rewrite this basically backwards and say that v of t is the derivative of x of t. Now I can apply the fundamental theorem of calculus in the exact same way as on the previous page. So what I have is an integral of the velocity function, v of t, with respect to time, let's say over some time interval from time 1 to time 2. Well, first of all, what I can do is what I've done before, replace the velocity function here with the derivative of the position function. So this integral is the same as the integral of x prime of t with respect to time over the exact same time interval. Now I have this expression here, and what the fundamental theorem of calculus tells me, let's take a quick peek at the previous slide, is if I have the integral and the derivative, then as I already mentioned, they basically cancel each other's actions, and all we get is the value of this inside function at the endpoint minus its value at the beginning point of the interval over which the integral was computed. So here, the integral and the derivative will cancel each other out, and all I'm going to get is the value of this position function at the end minus the value of the position function at the beginning. So that is x computed at the second point in the time measurements minus x computed at the first point. So what we have here is that the integral of velocity equals to the total change in position. Remember that the function x describes the position. This is the position at time t2 minus the position at time t1. The total change in position is also what we call a displacement. Notice that displacement is not the same as distance traveled. If I leave my house, go out for groceries, and come back in, my total displacement is the net change. My position at the end, which is my house, minus my position at the beginning, which is also my house, is in fact going to be 0. So my displacement will be 0, whereas my distance traveled is going to be obviously some number that is not 0. In order to visualize this on the graph, let's construct a quick little graph of what the velocity function would be and how we can combine this with the time as a variable. So what I was given in the beginning was the integral of the velocity function over the time interval between t1 and t2. So I have to have some kind of velocity function, let's say here it is, and 2 time points, t1, t2. We remember, of course, that the definite integral is always the area between the specified function and the x-axis between the two limits of integration. So in our case here, the integral on the left computes the area under the velocity curve between time 1 and time 2. Recall that the definite integral is a signed area. So if my velocity at any point was negative, for example, I was going away from my house and then toward it, this negative value would have counted against my total displacement. Now, this is a sketch of the left-hand side. What the right-hand side tells us is that this is exactly your displacement here. Let's see whether we can derive some formulas for various situations that the velocity can, in fact, for various values that the velocity can take. We're not going to be specific with numbers, we're just going to be specific with descriptions of the types of velocity that can take place. The simplest example is uniform motion with constant velocity. So this is something you can probably reason out even just with common sense or common logic, and we're going to go through this in a little bit more generality with integrals. So we're going to take the velocity to be constant. Let's say you're driving down the highway with a constant velocity of 90 kilometers per hour. If we take the integral of the velocity with respect to time directly, so using antiderivatives, what we're going to get is, think about what is the antiderivative of a number with respect to t. So what did you have to take a derivative of to produce just a constant? And that is, of course, that constant times your variable, vt. Now, this is a definite integral between 0 and t, so I have to evaluate it at those 2 points. Now, this is a bit confusing here because I called both of these values t, but I didn't want to introduce another variable. So I'm going to plug t in for t minus plug in 0 in for t. So I'm going to get vt minus v times 0, so simply vt. And this makes perfect sense. So this is the distance or the displacement traveled. If I, for example, drive with a velocity of 90 kilometers per hour, the units alone tell you it's a derivative because it's the rate of change. And I do so for the period of, let's say, between 0 and 2 hours. I would have to multiply the two together in order to produce the total displacement. And that's all this formula is telling me. Now, what we're going to do is think about this integral, but through the antiderivative of the velocity, which is the position function. So same as before, what that means is that this integral is actually the integral of the derivative of x, and then by the fundamental theorem of calculus, remember that the integral and the derivative cancel each other's actions, leaving me with the function itself to be evaluated at the endpoints. So this will give me x sub t minus x, or x of t minus x of 0. Now, x of 0 being the position at time 0 is often called the initial position, and because the initial position is something that's usually known, we denote it by x sub naught. Now, these two things, of course, have to be the same because they are, in fact, the exact same integral computed in two different ways. So what I'm going to do is equate these two expressions and see what that gets me. So what I have is that x of t minus x naught is equal to vt. And then, if I know my initial position, and I know the velocity that is a constant, and I know how long I have traveled for, that means that basically everything in this equation is known except for my position at time t. So I can solve this equation for the position at time t. And that is then going to be equal to my initial position plus vt. This is a formula that is often used in physics to describe the uniform motion with constant velocity. Now, and this is how you basically derive it. This makes perfect sense because what this is actually saying is that your position at time t equals to your initial position plus however much ground you've covered going at constant speed v for t period of time, right? So let's say you're traveling down the highway, your initial position is your x naught, you're traveling at a constant speed, like I mentioned, for example, 90 kilometers an hour times 2 hours. This is how far you've moved. This formula will tell you where you end up. This is the simplest case of constant velocity. Let's consider the next case, and that is constant acceleration. We see a lot of examples using constant acceleration in the context of falling objects, because then the constant acceleration is of course due to gravity, and that is something that we would really like to study for a variety of reasons. We're going to do the exact same thing, except for we're going to involve acceleration and velocity as opposed to velocity and the position, but these two are connected in the exact same way. They are an antiderivative. One is the antiderivative of another, and the other is the derivative of the first one. So we're going to go through the same process. We're going to assume that the acceleration is a constant called a. And first of all, we're going to take the integral directly. So again, here I'm going to have a times t to be evaluated between 0 and t. So at minus a0, and therefore at. And on the other hand, I note that acceleration is antiderivative of the velocity, which means that I can rewrite this integral in terms of the velocity, and then applying the fundamental theorem of calculus, integral and derivative cancel each other's actions. I get the velocity by itself to be computed at the endpoints of my interval. So v of t minus v of 0. And just like with the position function, v of 0 is often noted as v naught because this is something that is usually fairly known to us. I will now equate these two expressions, and overall I will then get that v of t minus v naught is equal to at. The exact same argument applies here. I normally will know my initial velocity, so for example, how hard I threw the object down towards the ground or away from the ground. I will know the constant acceleration that the object has, for example, due to gravity, and I also will know how long it's been falling for. What is unknown is the velocity at any given time t. So what this now formula tells me, again, the exact same kind of relationship as on the previous slide between the velocity and the position. What this says is the velocity at time t is equal to the initial velocity plus however much velocity you've gained due to accelerating for a fixed period of time. Now, because everything is a derivative or antiderivative of itself, given this expression, can we calculate the position function from this? And the answer is yes. We can go through this process again, but now with this as our initial assumption and our initial expression. So this is what we're going to do next. We have just computed this exact expression. V of t is v naught plus at. So we're going to go through these exact same setup, but with this slightly more complicated expression. So first of all, we note that the velocity is, or the position function is an antiderivative of the velocity. So once again, what I have is I can replace velocity with the derivative of the position, and I can then note that the integral and the derivative cancel each other out. I can plug in endpoints, and I will end up with x of t minus x naught. I'm calling it x naught right away. On the other hand, I'm going to take the integral of the velocity directly, but the velocity is given to me by this expression. So I'm going to replace the velocity with that expression here, v naught plus at, and take this integral directly with respect to time. V naught is a constant, so the antiderivative of a constant with respect to t is going to be v naught t, right? Like if this was a 5, and I'm taking the antiderivative with respect to time, I would get 5t plus at. A, again, is a constant, and t is my variable. So according to the product rule, I have to add 1 to the power and divide by that number, and I will also have this a as a constant remaining in the front. And this entire expression has to be evaluated between 0 and t. So t is my variable here. It's also the end of my integral. Again, I recognize the imperfect notation. I'm going to plug t in for t minus, I'm going to plug in 0 in for t to evaluate this integral. So what I'm going to get is v naught t plus I can leave this in the exact same form, minus, and then if I plug in 0, I notice that both of these terms turn to 0, so I'll just be subtracting 0, which obviously is like doing nothing, so I'm going to omit writing this down. And just like before, I'm computing two integrals that are the same, so I can set these two things to be equal, and what am I going to get? So equating, what are we going to get? We get x sub t, or x of t, minus x naught is equal to this expression. Instead of rewriting this twice, I'm actually just going to move x naught over to the right-hand side right away. So hopefully this is not too big of a step to follow. X of t is going to be x naught plus v naught t plus a t squared over 2. This is now my expression for the position function given the initial position, the initial velocity, and the constant acceleration. For those of you who have taken physics courses, this is usually a formula that you are given to start the unit on learning how the gravity works and how objects fall under gravity. In math courses, and now you can be pretty proud of yourself for having seen this process, we can derive, as we just did, this formula from first basics. So again, let's just note here what the formula says. The position at time t is given by the position that you start with, the initial position, plus whatever position you have gained during the fixed amount of time, starting with some initial velocity v naught, plus whatever you've gained according to the constant acceleration. Now, this is all great, and this is the first example of how the constant acceleration, and once again, likely one of the biggest contexts is acceleration due to gravity, works, and how you can calculate the position of a falling object using all of that information. However, this is the simplest setup and therefore not necessarily very realistic. This works fairly well if you drop an object from small height, but not very well if you drop it from anything above 1 or 2 meters. And that is, of course, because generally, acceleration of a falling body is not uniform due to frictional force introduced by air. So what we have here is that the acceleration is equal to the constant gravitational acceleration on Earth is, for example, 9.8 meters per second squared, minus what we call a drag, which depends on your velocity. The faster you're going, the more drag you are actually accounting. Now, let's try to rewrite this equation, but in terms of only one unknown function. Here I have gravity, which again is constant, so I know what the factor is. Here k is a constant of proportionality, and that will depend on the temperature and how thick the air is. But I do have two functions here, the velocity and the acceleration. Now, of course, we know that the acceleration is the derivative of the velocity, so we can use that to our advantage. Let's rewrite it as that. The velocity prime, which is the acceleration, is equal to g minus kv. If I remember that the velocity is a function of time, I can drop my t variable and end up with this as a differential equation. Does this look familiar? It should. It's exactly of the type we have seen before. It's exactly of the type a minus by, right? So this is fantastic news because we can actually solve this exactly. Now recall that the formula for the type a minus by was a bit complicated, but altogether the solution would then be that the function v of t is equal to, remember it was a over b, so g over k, minus a over b, so g over k, e to the power minus bt, so minus kt over here. I can factor out g over k because that's a constant, and altogether then I will have minus 1 minus e to the power of negative kt in the brackets here. This is it. This means that I can calculate the velocity of my falling object if I know the gravitational constant, the constant of proportionality of the drag, and the time at which I would like to actually compute said velocity. One interesting thing to ask is what happens as time goes to infinity? So if I drop the object in the same sort of air space and it falls for a very long period of time, what is going to happen to the velocity? If we are subtracting the velocity, the acceleration due to drag, is the velocity eventually going to be 0? Is there some kind of value that it will approach? Well, I can take the limit as time goes to infinity of my newly found velocity function, and let's see what we can come up with. So this is the same as the limit of this entire expression that I'm actually just going to copy over. Now, what can we analyze this with? Let's take a look. T goes to infinity, which means that this t goes to infinity. Now, the power on the e is negative here, so if you think of the graph of the exponential decay function, you will recall that it approaches 0 as the horizontal asymptote. That means that as time goes to infinity, this term approaches 0, and then altogether, I'm going to have g over k times 1 minus 0, so times 1, and therefore my limiting value will be g over k. This is what's known as the terminal velocity. So no matter how long you fall for, this is the terminal velocity that you will achieve as a falling object with a specific amount of drag. Notice that this doesn't depend at all on things like the initial velocity or the initial acceleration. It only depends on the constant acceleration that the body in question is under and the constant of proportionality of drag. The other interesting thing to compute is acceleration at the terminal velocity. Now I have the actual equation that allows me to calculate acceleration at anything. So let's take a look at what it's going to be in this case. Acceleration at terminal velocity. Let's plug it in and see. So my acceleration value is going to be, according to my equation, g minus k times v. So g minus k times z. But in this case, my v is my terminal velocity. So the value for v is g over k. I will plug this into here. And what am I going to get there? G minus k times g over k. Well, after some simplification, I'm going to notice that k's cancel out. I'm going to get g minus g, so overall 0. And that makes perfect sense. As time goes on, the terminal velocity is achieved, and the velocity is terminal at which the acceleration is also 0. The object is no longer accelerating and no longer decelerating. Now, do we have any real-life examples of dropping something from high enough to notice the effect or non-effect of the drag and the achievement of this terminal velocity? Well, luckily for us, Red Bull decided to put up a challenge and to see if a free-falling person could break the speed of sound while dropped from space. Let's take a look.
Start be moving here in a little bit. Let's get a little bit of release.
If you're scared, walk away, 'cause there's no need to feel ashamed. Yeah, we all feel the same. Where's your passion? Where's your fire
Alright, now the whole road is working on. I'm going over. Jumper away. Speed 725. Showing Felix in a stable descent.
So there are a couple of things in the video that you should pay attention to and maybe watch it over again. First of all, the Earth is in fact round. And second of all, when Felix is falling, Felix Baumgartner is the jumper's name, when he's free falling, he actually enters into a spinning pattern that was really worrisome because the gravitational centrifugal forces on him would have been so high that he was on the verge of passing out, which of course would have allowed him to not be able to open his own parachute, which is why the team somewhere in the middle of the video starts cheering the moment he's back straight up and not rotating. Now the question remains is if he actually broke the sound barrier. The speed of sound is 331 to 343 meters per second. There is an interval here because it actually depends on the air's temperature. Now, how can we figure that out? Well, they were measuring all kinds of things during the fall. In particular, they were, of course, measuring speed and altitude as a function of time and a whole bunch of other things. So we can take a look at the graphs and see what happened at which points of time that we should pay attention to. For example, one of the first graphs that they looked at was the speed as a function of time because we're wondering whether or not he achieved the certain speed. And we can see here that the highest speed achieved seems to be just above 350. So that most definitely beats the sound barrier. So they did achieve what they set out. But notice that while the speed increases up until that point as the jumper accelerates, after that is a pretty fast decline. So what happened at this point that caused such a dramatic turnaround? It's not like once you reach the speed of sound, you start decelerating greatly. So what we can look at here is what happened at that time on the altitude. If his highest speed was around here, let's just trace it down to our altitude function. So at around 50 seconds, my graphs seem to not be quite lined up. So let's just adjust that a little bit. There we go. At about 50 seconds, notice that the x-axis on both of those graphs is in fact the same. What we have is around 50 seconds is just around 30,000 meters. What happens 30,000 meters above Earth, above the surface of the Earth? 30,000 meters is about where he enters atmosphere. With atmosphere comes air, and therefore comes drag. This is the reason behind such a dramatic decrease here. So after that, he starts decelerating, as we've just shown, towards his eventual terminal velocity. And that is something else that we can look at. What is the speed of the jumper, Felix, and what is the terminal velocity? Notice that the terminal velocity also changes. It's not a constant because it really depends on air density and whatnot. So as time goes on, this tracks what the terminal velocity is and what is his actual velocity. Notice that in the end, they converge. So he reaches the terminal velocity before he actually reaches the surface of the Earth. But what the calculations that Red Bull had to do really is to take care of a few things. And the main one being that they lifted Felix Baumgartner high enough that he enters the atmosphere after achieving the speed of sound. Because in the atmosphere, achieving the speed of sound is basically impossible. The terminal velocity would not be possible to achieve there. Now, there are, again, this is how you would utilize the graphs to talk about things like the speed, the altitude, and the terminal velocity as compared to both of them. But let's come back and discuss how one would differentiate between the displacement and the actual distance traveled in relation with speed. The first one is the position of a car along the highway is given by this function, x, so the position in terms of time. We're asked to find the total displacement of the car in 1 hour. So again, remember that displacement is not even the distance traveled, it is simply the position at the end of the interval at which we're interested in, minus the position at the beginning. So over 1 hour means the position in 1 hour, because t is in hours, minus the initial position at hour 0. Now I can evaluate these by simply plugging in the corresponding t value into my position function. So it's going to be 100 plus 5 for the position in 1 hour minus x naught. Well, I can see if I plug in t equals 0, I'm simply going to get a 0. So altogether, I have 105, and the distance here is measured in kilometers. The next problem appears to be quite similar. Speed of a car along the highway is given by this velocity function in kilometers per hour over the first hour. We're asked to find the total displacement. So the exact same thing. Now here, speed is a function of time. So this previous method will not work because I don't know what the position actually is. And therefore, I'm going to have to think of something different. Now, the one thing to notice, of course, is that we can calculate the total distance traveled as the speed times the time. Now, this is the formula that we can use very easily if the speed is constant. So once again, back to my favorite numbers. If I drive for 90 kilometers an hour for 2 hours, in order to compute the total distance, I simply multiply the two together. Now, the difference here is that the speed is not constant, but rather given by some function that changes as time changes. So let's draw a little graph and see if we can figure out how we can attempt to understand the computations slightly differently. So let's say this is my velocity function v, so t versus v. And what I'm interested in, of course, is as time goes on, how much distance do I cover? So at any given time t here, if the distance or if the time interval is really, really small, then I can assume that over small time interval, let's call it delta t, for example, my velocity function was in fact constant. Constant in this case would mean a horizontal line. So I can assume that, for example, for 10 seconds at a time, my velocity doesn't change, or 1 second, whatever time interval you're comfortable with. The smaller, the better. Now, that means that what I'm actually interested in is the sum of these little time intervals where the velocity over that time interval is in fact constant. Here, the speed is constant, and the time is the small little chunk of time. So what I'm interested in overall is the sum of these little areas for when the velocity is in fact constant. Now this happens to be for very, very little time periods, and now I'm going to have to add them all up. So this brings me back to the sum of the area under the graph, in this case under the velocity graph, and this is again my definite integral. So the integral between whatever point that I'm interested in this case between 0 and 1, of the velocity as a function with time as the variable. So in this particular case, I would be interested in the 0 to 1 of the velocity function as given, so 100 t squared plus 5t dt, and if I actually find the antiderivatives, what am I going to get? The first one is going to give me 100 times t cubed over 3, plus the second one will be 5 t squared over 2. Evaluated between 0 and 1, I am going to get some kind of number. This is, again, another way to really understand how speed times the time will produce these little rectangles where if the time interval is taken to be very short, the velocity can be assumed to be constant. Now, what I end up calculating, though, is exactly what we've already talked about and is going to be true in general. Given the rate of change, such as velocity, the integral of it will produce total change, such as the distance or the displacement. Let's now take a look at an example that sort of unites the ideas that we've been discussing so far in this class. So what we have here is the graph of time versus velocity, similar to the graph that we've seen, for example, for the Baumgartner's example. And this is the position or velocities of two cars. Car number 1, let me maybe draw it in one color, say purple, whoops, and car number 2, which is a little bit different. The questions refer to how the cars interact with each other. So this is, let's say, data from a particular race. First, we have at what time or times do the cars have equal velocities? Since this is a velocity graph, this question is easy because all we have to do is figure out when are the two graphs at the same point. When do they intersect? And we see two noticeable points of intersection here and here. So we can say that it's approximately at time equals 0 and time equals 1. I'm going to approximate this to be 1. The next one, at what times do cars have equal accelerations? Now this is more complicated because I don't have the graph of an acceleration. I only have the graph of the velocity. So I have to interpret how to read acceleration from the velocity graph. Recall that acceleration is the derivative of velocity. So how can I interpret the derivative from the graph? What is a derivative of a given graph? A derivative is the slope of the tangent line. So what this question is essentially asking is when do the two graphs representing velocity functions have equal slopes? Meaning, when are they parallel? So you can think of the slopes of the first car, the slopes of the second car. Where do you see them being parallel? Well, I would say probably somewhere at around 3 is where the two tangent lines are parallel to each other. So equal slopes around 3. Which car is ahead after 1 minute? Which car is ahead after 3 minutes? Ahead means in terms of position. So this is now asking to come up with the way to describe position based on the velocity graph. Recall that the position is antiderivative of velocity, and what we've been discussing is that it is in fact area under the curve of the velocity function. So just like in the previous example here, we have to see what happens after 1 minute. So let's take a look at 1. What car has covered more area under the velocity curve by 1 minute? Well, I can see that the red car has covered this much, whereas the purple car has covered this much. So the purple car, car number 1, has clearly covered more area under the curve by 1 minute and therefore has covered more distance. After 3 minutes, so we are out here, now we gotta compare the areas collectively under each curve between 0 and 3. So the purple car has covered this much area, the red car has covered this much area, and now these are way harder to compare because they're such non-standard areas. One thing we can sort of see is that this is the difference between the coverage, and so maybe if I think that this piece is approximately equal to this piece, then up until nearly 2 seconds, or minutes rather, the two cars would have probably covered about the same distance. But then the car number 2 is going to cover that much more area than the car number 1. So the idea here is to try to think of when does this area get covered in the opposite direction, and therefore who is going to cover more ground afterwards. So once again, the position means that we're going to be comparing areas under curves of the velocity functions, and therefore after 1 minute we can see that the car that has covered more area under the curve is car 1, and after 3 minutes it's going to be car 2. The last question: when does one car overtake the other? Overtake, let's think what happens when two cars are racing and they overtake each other. This is my best attempt at a car. If they overtake each other, that means that the two cars at that moment are exactly at the same position. Same position means we're still comparing areas on the curves, and they have to be in the same spot. So when do the two areas under the curves equal? And we sort of answered that already in the previous part. It looks that they'll be equal at approximately 2 minutes because this area will compensate for this area and therefore provide equal coverage up until then. So let's record that. When do areas under the curves equal? And that is around 2 minutes. Analysis like this will prove really useful when you have a graph of a rate of change, but need to say something either about its derivative or its antiderivative without knowing the formula for the function itself. As a last example, let's take a look at what happens when we do have a formula and are asked to compute two different things with it. So here I have that a mail truck delivers mail to various companies along the central avenue, so going back and forth, and this is its velocity function. First, we're asked to find the displacement. The displacement is always straightforward. All we have to do is take the integral of the velocity function that is given to us here. So the integral of t squared minus 9t plus 14, because the displacement is simply the final position minus the beginning one over the time interval at which we're interested at. On the other hand, in part 2, we're asked about how much gasoline was consumed. So we're not interested in displacement, because if the truck starts at his house and returns to his house, the displacement will be 0. Here, we need to find the total distance traveled first. And this is going to be a little trickier, because this is now going to require us to think about when is the velocity positive and when is the velocity negative. Let's sketch this function to see what actually happens to the graph of it. So here, first of all, it's a quadratic formula, or it's a quadratic function, which means that I should be able to factor it out or figure out that it doesn't have roots. If I think about this for a second, I can see that it factors nicely into t minus 2, t minus 7, which now means that I can sketch it fairly reasonably. I have a parabola looking up that goes through points 2 and 7. So my sketch has to be something that looks like this. And now I can see that the velocity, remember this is my velocity function, velocity was positive up until 2, so the distance covered will correspond to the area under the curve here. Then the velocity was negative, so the distance covered will correspond to the area above the graph here. And then, because we're interested to go until 10, the velocity after 7 till 10 is going to be positive again, and therefore correspond to the area covered there. Now that means that I will have to make sure that my integral on the portion where the function is negative will get negated in order to produce a positive result. So that means that in my computations for distance traveled, I will have to compute the integral of my velocity function between 0 and 2. That integral I know to be positive because the function is above the x-axis. Then I'll have the integral between 2 and 7. Now, a priori, I know that this integral is going to be negative, but I would like to count the distance positively, so that means that I have to negate the known negative integral in order to produce a positive result. And then between 7 and 10, as seen from the graph, I know that the velocity is going to be positive again, so it will count positively once again. So this is it. We can compute these integrals. The function, the velocity function, can go into each one. You can take an antiderivative and plug in the points. This will give you distance traveled. And then in order to figure out how much gas will be consumed, you simply have to multiply the distance by the gas consumption of this particular mail truck. I trust you'll be able to actually finish off this question on your own time to further practice taking antiderivatives, combining things together, and then looking back at the graph to make sure you understand where each piece of the distance traveled formula came from.